All right, section 6.3 is quantum numbers, orbitals, and probability patterns. One objective here, be able to state the relationship between the principal quantum number, which is n, the number of orbitals, and the maximum number of electrons in the principal energy level. All right, so we were talking in the last section about Schrodinger's equation, that big fancy equation, and it worked in almost every example. It worked really well. But it was really hard for scientists to kind of visualize what does that mean that electrons are running around in a wave. What exactly does that tell us? We don't, it's hard to visualize that or think about that. So another scientist named Max Born used these equations and used them to find the probability. So he says, hey, this is the likelihood of where the electron is going to be. We think it's going to be in here, in this area. That's our probability of finding the electron. That's kind of what he used. Think of it as taking a snapshot of where the electron was every second. So if you did that, if you took that snapshot, you would get something like this, where, these darker areas in here, that kind of says, hey, that's where the electron is most of the time. And the lighter areas around the outside, out here, hey, it's not there very often, okay? So this kind of shows you the probability of where we're going to see it. And you can see the electron's more likely to be inside there than to be outside of there. And usually what they did was they said, hey, let's set that boundary at about 90%. So in other words, there is no real boundary for this. Just understand that. The electron can be anywhere. But for us, we set this idea that, hey, the electron is going to be inside of that sphere 90% of the time. They usually use that boundary of 90%. So they look at where the electron is, kind of plot those points, and then kind of find an area and say, hey, this is where it is 90% of the time. 10% of the time it's going to be outside of that, and we're not going to worry about what that's going to be like, but we're worried about what does it look like in the area where it is 90% of the time. And when you come up with that and you figure out where these electrons are, if you kind of solve Schrodinger's equations, you come up with 4 special numbers, which we call quantum numbers. And that's, we're not going to sit and solve those equations. In this particular chapter, we don't have any equations that we're really going to use. What you just need to know are some information about, this stuff. So in other words, we need to understand, what are they talking about when they're talking about the principal quantum number? What does that mean? But we're not worried about how we solve that and where we get it, except in general, but we're not going to solve those equations. But those 4 numbers will completely describe the energy that an electron has. And that energy is related to its wave and so on. Another scientist named Pauli came up with what's known as the Pauli exclusion principle. Says that no 2 electrons can have the same 4 quantum numbers. So in other words, every electron is identified differently in an atom with those quantum numbers. So with those 4 numbers, you can say, hey, I'm talking about that particular electron, that it's right here, it's in this place, it's in this level, in this sublevel, and so on. All right, so what do they mean? Well, the principal quantum number, when we were talking about the Bohr model, and we drew the little circles around the atom. So, here's my nucleus, and then I drew the circle. Okay, that first circle would be that first quantum number, and that would be level 1. Okay, if I drew a second circle, that'd be level 2. Now remember, we've gone away from this planetary model. We're in the idea of these clouds and so on. But we're still talking about the principal number, and that's n. And you can kind of relate it back to these circles, so a third circle, hey, that'd be level 3. That'd be n equals 3 then if I was talking about some electron that's out there. So these principal numbers, use n. So whenever you see them talk about n now, they're talking about that principal quantum number. And, that could theoretically go on to, any number of the elements that we know right now. The quantum number goes up, the highest is 7. And then, Nothing goes beyond that because we would need more elements on the periodic table to describe those.